Hello, my name is Josh Feliciano, and the title of this presentation is an LM34-based Ambient Temperature Sensor Circuit, a circuit to display ambient temperature in degrees Celsius and in degrees Fahrenheit via multimeters. I hope it is clear that I want to talk about a circuit as a temperature sensor that displays ambient temperature in the most used units. I will be discussing the design, testing, problems, and solutions involved with creating this circuit, with a focus on justifying the use of the number of required operational amplifiers. Designing anything should involve clearly defined goals. A design goal for this project involves the readings of two digital multimeters, or DMMs. The goal is to have a 1 millivolt reading be equal to 1 degree Celsius or 1 degree Fahrenheit, depending on which digital multimeter is being observed. The second design goal is to limit the number of operational amplifiers, or op-amps. Doing this will lower the cost of the circuit because op-amps are expensive when compared to passive components. Another goal is to have an accurate reading such that the reading is within plus or minus 0.1 degrees from the actual ambient temperature. It seems that a satisfactory accuracy can be achieved with 3 op-amps, but I'll get into that later. The final major design goal has to do with making the sensor as useful as possible. One way to improve the utility is to maximize the temperature range so that the circuit can be used in a variety of environments. The maximum range depends on component limitations. Speaking of limitations, we are restricted to the LM34 IC temperature sensor and to micro alpha 741 op-amps. The LM34 has a specified operating temperature range of minus 50 degrees Fahrenheit to 300 degrees Fahrenheit in free air, which is about minus 45.556 degrees Celsius to about 148.889 degrees Celsius. The Micro Alpha 741C op-amp has a relatively small temperature range of 32 degrees Fahrenheit to 158 degrees Fahrenheit, or 0 degrees Celsius to 70 degrees Celsius. But fortunately, the Micro Alpha 741M op-amp has a range of minus 67 degrees Fahrenheit to 257 degrees Fahrenheit, or minus 55 degrees Celsius to 125 degrees Celsius. In the end, this means the specified operating temperature range of the circuit is minus 50 degrees Fahrenheit, or about minus 45.556 degrees Celsius, to 257 degrees Fahrenheit, or 125 degrees Celsius. Another restriction concerns the availability of resistors. Resistors of 24 5% standard values are available, which include decade multiples from 10 ohms to 22 mega ohms. The specific values are in a table at the end of this presentation. Moreover, the last restriction is the fact that DC power is available only at positive 15 volts and at negative 15 volts. With goals and restrictions more clearly defined, design can be continued. For example, here's the block diagram from which the circuit is based. First, the LM34 outputs to a voltage divider. This voltage divider then provides properly scaled voltage to the digital multimeter to display 1 millivolt as 1 degree Fahrenheit. Moving to the Celsius section, the LM34 also outputs to a summing amp. Furthermore, the second input to the summing amp starts as the positive 15 volts of the DC power supply. It is then divided down, buffered, and sent to the summing amp. The summing amp effectively performs the first operation of the conversion from Fahrenheit to Celsius, which includes deducting 32 from the temperature in degrees Fahrenheit. From there, a fixed gain amp completes the conversion to Celsius and properly scales the voltage by multiplying the input voltage by 1/18. The output is then sent to the multimeter such that 1 millivolt is 1 degree Celsius. Okay, so this is the actual testing circuit. First I want to point out the resistor values are all 5% standard values, and this can be verified with the table at the end of the presentation. Looking up here in the upper left corner, we have the LM34. Now this is actually a stand-in model because there is no LM34 component, but I'll talk about that later. Going over to the right, from the output of the LM34, we have this connection. This connection is required for full range use of the LM34, and the resistor value here can be determined by taking the negative DC voltage supply and dividing that by 50 microamperes, and in this case we are left with 300 kiloohms. So going over to the right again, we can either go down to the Celsius section or right to the Fahrenheit section. Fahrenheit section is pretty basic. It's only a voltage divider, and it will have a multiplier of 20 over the quantity 20 plus 180, which is 20 over 200, which is 1/10. So output voltage will be 1/10 of input voltage. Therefore, this reverses the multiplication by 10 over at the LM34 by dividing by 10. So we get the correct scale at the Fahrenheit multimeter here. So going over to the Celsius section, let's look down in the lower left corner at the positive 15 DC volts. This voltage gets reduced by a voltage divider with a multiplier of 820 ohms over the quantity 36 kiloohms plus 1.5 kiloohms, which will result in a output voltage of 320 millivolts. It's actually 328 millivolts, but this is acceptable for the circuit's operation. So going over to this micro alpha 741 MJG, we see that it's operating as a buffer for this voltage divider, and it has an input resistor of 820 ohms and a feedback resistor of 820 ohms. Therefore it has no gain. All it does is buffer and invert the 320 millivolts. This inversion is good for the summing amplifier because it causes subtraction, which is necessary for the conversion to Celsius. And we can see that there is no gain because the feedback resistor and the two input resistors are the same values. Going over to the right again, we come across another micro alpha 741 MJG. This one is acting as an inverting fixed gain amplifier with a constant of 1 over 18, which completes the conversion to Celsius while also putting the voltage in the correct scale. And that is output to the Celsius multimeter up here, where 1 millivolt will equal 1 degree Celsius. With the circuit built, discussing accuracy seems like the next logical step. In this case, accuracy or temperature error is defined as the actual ambient temperature subtracted from the associated reading. Temperature samples were taken at the temperature limits. Samples were also taken from negative 45 degrees Celsius to 125 degrees Celsius at intervals of 5 degrees Celsius. We can see in this first graph that the maximum temperature error is a mere 0.014 degrees Celsius, which is well within the 0.1 degree limit. This second graph is for the degrees Fahrenheit portion of the circuit. The same sampling method was employed, revealing an absolute maximum temperature error of 0.024 degrees Fahrenheit. Again, this is within the 0.1 degree goal. Allow me to take this opportunity to try and justify the use of 3 op-amps. With more voltage divider portions, a similar temperature sensor circuit is possible with 2 op-amps or even 1 op-amp. Yet a circuit of 1 op-amp results in a maximum absolute temperature error that is significantly higher than 3 degrees, while a circuit of 2 op-amps results in a maximum absolute temperature error that is higher than 0.2 degrees. These larger errors are due to the effects of loading. Therefore, 3 op-amps are necessary because they buffer sections of the circuit to minimize loading effects, thus ensuring a low temperature error. A handful of challenges were encountered during this project. For instance, poor communication between team members was a problem, although it seems this was mostly due to unavoidable personal issues. To try to remedy this, I put forth my best effort to collaborate, but in the end, I decided this project would be best as a personal challenge, and I therefore took the decision to continue alone. Moving on, unexpected component limitations were also challenging. For example, operating temperature ranges. Since only specific components were available, the temperature range of the sensor had to be adjusted as a remedy. A last challenge presented itself in the form of a lack of a simulation model for the LM34. This is the stand-in subcircuit for the LM34, and it is a near ideal model used to solve the problem of the missing LM34 component. The subcircuit is based on an analog behavioral model voltage source that converts the ambient temperature of the simulation environment in degrees Celsius to an output voltage that reflects ambient temperature in degrees Fahrenheit. This model is nearly ideal because it outputs a voltage that is practically equal to the ambient temperature of the simulation environment in Fahrenheit times 10 millivolts per degrees Fahrenheit. But it is not completely ideal because it uses the typical output resistance of a 1 milliamp load, resulting in a more realistic simulation. Before finishing this presentation, I should note that because of the near ideal LM34, the simulation is likely more accurate than its real-life counterpart. Fortunately, the LM34 is quite accurate. That is, a maximum temperature error of plus or minus 1 degree Fahrenheit for the full range of the device. And for that reason, the results of the simulation should be satisfactorily similar to the results expected from a real circuit. And that concludes the presentation. As a final note, I hope it is now clear that I have presented a circuit for sensing and displaying ambient temperature in degrees Fahrenheit and in degrees Celsius. This circuit is highly accurate, it has a maximized operating temperature range given the available components, and it uses a minimum number of op amps to achieve its high accuracy. And that's the gist of it. Thank you for your attention.